In this lecture we'll find out the length of chord BC. In the drawing we have a semicircle. We know that the center of this semicircle is at this point O. Inside this semicircle we have square DEFO, and we know that the area of this square is equal to 5 square units, and our mission is to find out the length of this chord called CB or BC. Okay? So first of all, we know that DEFO is a square, and we know that all the angles inside any square are right angles. That is to say, those 4 angles, they are all right angles. They are equal to 90 degrees. So we can right here, this angle, those 2 angles, they are all right angles. They are equal to 90 degrees. Those 2 angles, they are also right angles. They are equal to 90 degrees. And we know that the area of any square of this square equals to, this is a square, the length of the square times the width. Okay, but because of the fact that the length and the width are the same, because of the fact that all the sides of any square are equal to each other, we can say that the area of this square is equal to one side times the other side, or the area of this square. Here the square brackets is the sign for the area. The area of this square equals to the side squared. Okay. So the area of our square DEFO, the area of square DEFO is equal to the side times the side. That is to say, the area of square DEFO equals to the side squared. But we know it is given us in the question that the area of this square DEFO equals to 5 square units, so we can substitute the area by 5. That is equals to the side squared. Here we will take a root out of this equation, and we find out that one side of square DEFO equals to the square root of 5 units. So all the sides of the square are equal to each other. They are all equal to the square root of 5 units. In the next step, we will join points D and O together by a straight line. Triangle DOF is a right triangle. The green triangle is a right triangle. Therefore, we can implement the Pythagoras theorem of the green right triangle DFO. So we copy the right green triangle DFO in a new page. and we'll implement the Pythagoras theorem on this right triangle DFO. So actually, this is the right triangle DFO that I copied from the original drawing. Side DF equals to side FO, they are all equal to the square root of 5 units. They are of the sides of the square. This angle equals to 90 degrees because it is one angle of the square, and we know that all the angles of the square are right angles. So here by PT, that is to say, it is a relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of this triangle DFO is DO, therefore the square of the hypotenuse is DO square. And it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to DF square plus FO square. So according to the Pythagoras theorem, DO square equals to DF square plus FO square. So DO square, that is the square of the hypotenuse, equals to DF square. DF equals to the square root of 5, therefore DF square equals to the square root of 5 square plus FO square. FO also equals to the square root of 5, therefore FO square equals to the square root of 5 square. So DO square equals to the square root of 5 square is of course 5 plus the square root of 5 square is 5. So in conclusion we found out that DO square equals to 5 plus 5, that is 10. Here we'll take a root out of this equation and we'll get that DO equals to the square root of 10 units. Therefore the hypotenuse is square root of 10 units. But DO, it is the hypotenuse of the green triangle. In addition, what is the definition of DO? Line segment DO starts from point O, that is the center of the semicircle, and ends at point D, that is a point on the semicircle itself. This is exactly the definition of a radius. That is to say, DO is the radius of the semicircle that is equal to square root of 5 units. The radius of the semicircle equals to the square root of 5 units. What is the definition of line segment OB? Line segment OB starts from the center of the semicircle, that is to say from point O, and ends at point B, that is a point on the semicircle itself. This is exactly the definition of a radius. That is to say, OB is the radius of the semicircle that is equal to the square root of 10 units. Likewise, OA, it starts from point O, that is the center of the semicircle, and ends at point A, that is a point on the semicircle itself. Therefore, OA is the radius of the semicircle that is equal to the square root of 10 units. Okay. In the next step, I will present to you a new rule, and we'll implement the new rule in our drawing. According to the new rule, this is actually rule number 1. The sum of the angles on one side of a straight line is equal to 180 degrees. So what is the meaning of this rule? Actually, the meaning of this rule is that if we have a straight line, AB is a straight line, and we choose any point on this straight line. If this is point K, we have here side KL, so if we focus on the upper side of the straight line AB at point K, that is, the upper side is one side of this straight line, because the straight line AB has two sides, the upper side and the lower side. So the sum of the angles on the upper side of the straight line AB at point K must be equal to 180 degrees. That is to say, this angle plus this angle, in total, the sum of those two angles must be equal to 180 degrees. This angle is angle AKL, plus this angle is angle LKB. In total, the sum of those two angles must be equal to 180 degrees according to this rule, rule number 1. The same thing is true, the sum of the angles on one side. This one side is the upper side. The same thing is true in the lower side. That is to say, the sum of the angles in the lower side of the straight line AB must be equal to 180 degrees. That is to say, in the lower side we have this angle. At point K we have this angle. In the lower side of AB at point K we have this angle. This angle, it is also equal to 180 degrees. So we actually can implement this rule number 1 in our drawing. Why? Because in our drawing we know that this is a semicircle and AB is the diameter of the semicircle. Okay, in any semicircle, always AB is the diameter of the semicircle. So AB is the diameter of the semicircle. It is absolutely a straight line. Okay, so AB is a straight line. So if you focus on the upper side of the straight line AB at point O, here the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of AB at point O? We have this angle, that is the right angle, it is equal to 90 degrees, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule number 1. 90 degrees plus the missing angle equals to 180 degrees. So the missing angle must be equal to 180 degrees. Very simple. In order to complete the sum of the angles on the upper side of AB at point O to 180 degrees, the missing angle must be equal to 90 degrees. So that is to say, angle EOB equals to 90 degrees. And because of the fact that angle EOB equals to 90 degrees, it means that triangle EOB is a right triangle. So the pink triangle EOB is a right triangle. So we can implement the Pythagoras theorem on the right pink triangle EOB. According to the Pythagoras theorem, on the right pink triangle EOB, so I'll copy the right pink triangle EOB in a new page and we'll implement the Pythagoras theorem on this right triangle. So this is the right triangle EOB that I copied from the original drawing. This right big triangle. So we will implement the Pythagoras theorem on this right triangle EOB by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse in any right triangle equals to the sum of the squares of the perpendiculars. The hypotenuse is EB, therefore the square of the hypotenuse is EB squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO squared plus OB squared. Again, according to the Pythagoras theorem, on this right triangle EOB, EB squared equals to EO squared plus OB squared. So EB squared, that is the square of the hypotenuse, must be equal to EO squared. EO equals to the square root of 5, therefore EO squared equals to the square root of 5 squared plus OB squared. OB equals to the square root of 10, therefore OB squared equals to the square root of 10 squared. So in conclusion, we found out that EB squared equals to the square root of 5 squared plus square root of 10 squared. So EB squared equals to the square root of 5 squared, it is equals opposed to 5, plus the square root of 10 squared, it is equal to 10. In conclusion, we found out that EB squared equals to 5 plus 10 is 15. We'll take a root out of this equation, and we'll get that EB equals to the square root of 15. The hypotenuse EB equals to square root of 15 in its length. Here EB equals to the square root of 15 units. Our mission is to find out the length of this chord called CB. We have already found out that EB equals to the square root of 15 units. The only thing that is left to find is to find out the length of line segment CE. In order to find out the length of line segment CE, we will, in the first step, we will complete this semicircle to a circle. So we actually completed the semicircle to a circle. In the next step, we will extend OE on both sides. That is to say, we will extend OE towards the upper side until it touches the circle. At this point, we define the touching point of the extended OE and the circle as point M. In the next step, we will extend line segment EO by a straight line until it touches the circle. At this point, we'll define the touching point of the extended EO and the circle as point N. So what is exactly line segment NO? Line segment NO starts from point O, that is the center of the circle and the semicircle also, and ends at point N, that is a point on the semicircle, or the circle itself. That is exactly the definition of a radius. That is to say, ON is the radius of the circle, that is also equals to the radius of the semicircle, that is equal to the square root of 10 units. And likewise, we know that point O is the center of the circle, point M is the point on the circle itself, therefore OM is the radius of the circle and the semicircle, that is equal to square root of 10 units. We know that EO equals to square root of 5 units. So from the drawing, it is very easy to see that ME, the length of this line segment ME, it is equal to MO minus EO. Again, ME equals to MO minus EO. So I write it down. The length of line segment ME equals to MO minus EO. So ME equals to MO. We know that MO equals to square root of 10 units. That is the radius of the circle and the semicircle. And EO equals to square root of 5 units. So in conclusion, we found out that ME equals to the square root of 10 units minus square root of 5 units. Okay, here ME equals to the square root of 10 units minus square root of 5 units. What is the length of line segment EN? It's very easy to see from the drawing that EN equals to EO plus ON. Again, EN equals to EO plus ON. I'll write it down. EN equals to EO plus ON. So EN equals to EO, that is square root of 5 units, plus ON, that is square root of 10 units. So in conclusion, we found out that EN equals to the square root of 10 units plus square root of 5 units. We have already found out that ME equals to the square root of 10 minus square root of 5, and finally we have already found out that EB equals to the square root of 15 units. Okay. In the next step, I will present to you a new rule that will be rule number 2, and we will implement rule number 2 in our drawing. Okay, so according to rule number 2, rule number 2 is true in any circle. So I write down here, in any circle. So the circle that I will draw could be any circle. If we have chord AB, this is chord AB inside the circle that intersects with chord CD, this is also inside the circle. This is called CD. The intersection point is at this point. We define the intersection point as point O. So I write it down. If chord AB intersects with chord CD at point O, you can see here that chord AB intersects with chord CD in the red line at point O. Point O is the intersection point of the two chords. Then the following equation will be true, that AO times OB, AO times OB equals to AO times OB equals to CO times OD. CO times OD. Repeat again. If chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN. This is called MN that intersects with chord CB. This is called CB. It's point E. The intersection point between the two chords is at point E. Therefore, according to the new rule number 2, we'll get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. So I will copy the two chords that intersect with each other in a new page, and we'll implement rule number 2 in our new drawing. According to the original drawing, we can see that chord MN passes through the center of the circle, that is to say from point O. So we have chord MN. This is chord MN. That intersects with chord CB. This is called CB. And the intersection point occurs at point E. This is the intersection point between the two chords. So I write it down. In our original drawing, chord MN intersects with chord CB at point E. Repeat again, chord MN intersects with chord CB at point E. Therefore, according to rule number 2, we'll get that ME times EN equals to CE times EB. CE times EB. Repeat again, chord MN intersects with chord CB at point E. Point E is the intersection point between the two chords. Therefore, according to rule number 2, ME times EN equals to CE times EB. We've already found out that ME equals to the square root of 10 minus square root of 5. We've already found out that MN equals to square root of 10 plus square root of 5. We have already found out that EB equals to the square root of 15. The only missing line segment is line segment CE. So we can write down inside this formula that ME, you can substitute ME by square root of 10 on square root of 5. EN equals to the square root of 10 plus square root of 5. And it is equal to CE, that is the missing line segment, so we leave it as it is, times EB. We've already found out that EB equals to the square root of 15 units. So here we can change the order. Why? Because A times B equals to B times A. Okay, so we can write down that square root of 10 plus square root of 5 equals to square root of 10 minus square root of 5. and it is equal to CE times square root of 15. In order to find out the value of this expression, square root of 10 plus square root of 5 times square root of 10 minus square root of 5, we will use the algebraic identity that states that a plus b times a minus b equals to a squared minus b squared. According to this algebraic identity, in our specific expression, a equals to the square root of 10 units, b equals to the square root of 5, and we know that a plus b times a minus b equals to a squared minus b squared. That is to say, this expression equals to a squared minus b squared. A equals to square root of 10, therefore a squared equals to the square root of 10 squared, that is 10, minus b squared. B equals to the square root of 5, therefore b squared equals to the square root of 5 squared, that is 5. So in conclusion, we found out that a squared minus b squared in our specific expression equals to 10 minus 5, and we know that according to rule number 2, this expression equals to CE times square root of 15. 10 minus 5 is 5, so 5 equals to CE times square root of 15. Here we will divide this equation by square root of 15, and we will get that CE equals to 5 over square root of 15. Okay, so we actually found out that CE equals to 5 over square root of 15. We are looking for the length of chord CB. It's very easy to see from the drawing that CB equals to CE plus EB. Again, CE plus EB equals to CE plus EB equals to CB. I'll write it down. From the drawing it is very easy to see that CB, the chord that we are looking for, equals to CE plus EB. So CB equals to CE. We just right now found out that CB equals to 5 over square root of 15 plus EB. We have already found out that EB equals to the square root of 15 units. So in conclusion, the answer to our question is that the length of this chord CB, it is equals to 5 over square root of 15 plus square root of 15. Again, CB equals to 5 over square root of 15 plus square root of 15. Now we will simplify this expression because we don't want to have a square root in the denominator. Therefore, we'll multiply square root of 15 by square root of 15, and then we'll divide it by square root of 15. Square root of 15 over square root of 15 is 1, so we can multiply square root of 15 by 1, because in this way we'll change nothing. Any number that is multiplied by 1 remains the same number. So CB equals to 5 over square root of 15. Here we will multiply square root of 15 by square root of 15, and then we'll divide it by square root of 15. So we get that CB equals to 5 plus square root of 15 times square root of 15 is 15 over square root of 15. So in conclusion, we found out that CB equals to, in the numerator we have 5 plus 15 is 20 over square root of 15. Okay, again we don't want square root in the denominator, so we'll multiply this expression by square root of 15, and then we will divide it by square root of 15. So we get that CB equals to 20 over square root of 15. Again, we'll multiply this expression by square root of 15, and then we divide it by square root of 15, so we change nothing because we multiply it by 1. So we'll find out that CB equals to 20 times square root of 15 over square root of 15 times square root of 15 is 15. So we found out that CB equals to 20 times square root of 15 over 15. Here we will divide this expression, both the numerator and the denominator, by 5. Here 20 over 5 is 4. So in total, in the numerator we have 4 times square root of 15 over 15 over 5 is 3. So in conclusion, we found out that the length of this line segment or chord CB equals to either 4 times square root of 15 over 3 units, or in terms of numbers, it is equals to 5.164 units. Okay? So, we finished with the question. In the next step, I'll summarize the lecture. So in the original drawing, we had a semicircle. We know that the center of this semicircle is at point O, this point. Inside this semicircle, we have square DEFO. We know that the area of this square is equal to 5 square units, and our mission is to find out the length of this chord CB. Okay? So first of all, because of the fact that DEFO is a square, all the angles inside any square are right angles. So those 4 angles, they are all right angles. They are equal to 90 degrees each one. And then we also know that the area of a square equals to the length times the width. But because of the fact that in any square the length equals to width, we can write down that the area of any square equals to the side times the side. Okay? Or the area of any square equals to the side squared. Right? Because all the sides of any square equals to each other. So the area of square DEFO equals to side times side. The area of square DEFO equals to side squared. But we know it is given us the question that the area of square DEFO equals to 5 square units. So we can write down that the area, we can substitute the area by 5, and 5 equals to side squared. We will take a root out of this equation, and we get that the length of one side equals to the square root of 5 units. That is to say, the area of all the sides of this square are equal to square root of 5 units. Okay, so in the next step, we will join points D. We join points D and O together by a straight line. By joining points D and O, we created the right green triangle DFO. This angle equals to 90 degrees because it is one out of 4 angles of the square. They are all equal to 90 degrees. So here we can implement the Pythagoras theorem of the right green triangle, triangle DOF. So I copied the right green triangle DOF in a new page. This is the right triangle DOF that I copied from the original drawing. You know that DF equals to FO. They are both the sides of the square that are each of them equals to the square root of 5 units. The only thing that is left to find is to find out the value of the hypotenuse DO. We will use the Pythagoras theorem in order to find out the value of the hypotenuse. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle is DO, therefore the square of the hypotenuse is DO square, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to DF square plus FO square. That is to say DO square, that is the square of the hypotenuse, must be equal to DF square. DF equals to the square root of 5, therefore DF square equals to the square root of 5 square plus FO square. FO also equals to the square root of 5, therefore FO square equals to the square root of 5 square. So in conclusion, we found out that DO square equals to the square root of 5 square plus square root of 5 square. That is to say, DO square equals to the square root of 5 square. The square root of 5 square equals to 5, so it is 5 plus 5. 5 plus 5 is 10, so we found out that DO square equals to 10. We took a root out of this equation and we found out that DO, that is to say the length of the hypotenuse DO, equals to the square root of 10 units. Okay? Here, the hypotenuse DO of the green triangle equals to the square root of 10 units. What is actually, we know that DO is the hypotenuse of the green triangle, but we know that line segment DO starts from the center of the semicircle and then that point D, that is the point of the semicircle itself. That is exactly the definition of a radius. Therefore, DO is the radius of this semicircle. Therefore, it is, and we know that it is equal to square root of 10 units. Okay? Likewise, if we focus on line segment OB, line segment OB starts from the center of the semicircle, that is to say from point O and then says point B. That is a point on the semicircle itself. Therefore, OB is the radius of the semicircle that is equal to the square root of 10 units. Likewise, if we focus on line segment OA starts from point O, that is the center of the semicircle, and ends at point A, that is a point on the semicircle itself. Therefore, OA is the radius of this semicircle that is equal to the square root of 10 units. So, in the next step, I presented to you a new rule, that is actually rule number 1, and we implemented rule number 1 in our drawing. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. So, AB, if AB is the straight line, we'll choose any point on the straight line AB. Suppose that the point that we choose is point K. Here we have side KL. So if we focus on the upper side of AB, that is the upper side of AB, it's point K. We know that according to this rule, rule number 1, the sum of the angles on the upper side of the straight line AB at point K must be equal to 180 degrees. So the sum of those two angles must be equal to 180 degrees. Why? Because in one side the sum of the angles is equal to 180 degrees. So if we choose the upper side of the straight line AB at point K, the sum of the angles must be equal to 180 degrees according to this rule, rule number 1. That is to say, the sum of those two angles must be equal to 180 degrees. This angle equals to, it is angle AKL, plus this angle, that is angle LKB. So angle AKL plus angle LKB must be equal to 180 degrees according to this rule, rule number 1. The same thing is true if we focus on the lower side of the straight line AB at point K. Here the sum of the angles must be equal to 180 degrees. So this angle, it is also equals to 180 degrees. We can implement this rule number 1 in our drawing. Why? Because in our drawing, you know that this is a semicircle, and AB, it is always the diameter of the semicircle. AB is the diameter of the semicircle, it is absolutely a straight line. So if we focus on the upper side of the straight line AB at point O, here the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of AB at point O? We have this angle that is equal to 90 degrees plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees. So the missing angle here must be equal to 90 degrees. In order to complete the sum of the angles on the upper side of AB at point O to 180 degrees, the missing angle must be equal to 90 degrees. It's very simple. It is one variable in one equation. Okay, so the missing angle must be equal to 90 degrees. And because of the fact that angle EOB, this angle equals to 90 degrees, it means that the pink triangle EOB is a right triangle. Therefore, we can implement the Pythagoras theorem on the pink right triangle EOB. So I copied the right pink triangle EOB in a new page, and we implemented the Pythagoras theorem on this pink right triangle EOB. So this is the right pink triangle EOB that I copied from the original drawing. Okay. Here we have already found out that EO equals to the square root of 5 units. This is one side of a square. We have already found out that OB, it is the radius of the semicircle that is equal to the square root of 10 units. This angle equals to 90 degrees according to rule number 1. The only missing thing is the hypotenuse CB. We can implement the Pythagoras theorem on this right triangle in order to find the length of the hypotenuse CB. The length of the hypotenuse AB. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendicular. The hypotenuse is AB, therefore the square of the hypotenuse is AB squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO squared plus OB squared. So in conclusion, we found out that EB squared equals to EO squared plus OB squared. So EB squared equals to EO squared. EO equals to the square root of 5, therefore EO squared equals to the square root of 5 squared plus OB squared. OB equals to the square root of 10, therefore OB squared equals to the square root of 10 squared. So EB squared equals to the square root of 5 squared, that is 5, plus square root of 10 squared, that is 10. So in conclusion, we found out that EB squared equals to 5 plus 10. 5 plus 10 is 15. So we found out that EB squared equals to 15. We took a root out of this equation, and we found out that EB equals to the square root of 15 units. So the length of the hypotenuse EB equals to the square root of 15 units. So we can write down here in the original drawing that EB, here 9 segment EB equals to the square root of 15 units. We are looking for the length of chord CB. We have already found out that EB equals to the square root of 15 units. The only thing that is left to find, in order to find out the length of CB, is to find out the length of line segment CE. In order to find out the length of line segment CE, we completed the semicircle, this semicircle to a circle, and then we extended EO on both sides. We extended OE towards the upper side until it touches the circle at point M. Point M is the touching point between the extended OE and the circle. Then we extended EO towards the lower side by straight line until it touches the circle at point N. Point N is the touching point between the extended EO and the circle. So what is actually line segment ON? Line segment ON starts from the center of the circle and ends at point N, that is the point of the circle itself. This is exactly the definition of a radius. That is to say, ON is the radius of the circle that is equal to the square root of 10 units. Okay, so and what is the length of En? Here En, it is very easy to see that En equals to EO plus ON. Again, EO plus ON equals to En. Okay, so En equals to EO, that is square root of 5, plus ON, that is square root of 10. In conclusion, again, En equals to EO plus ON, so En equals to EO, that is square root of 5, plus ON, that is square root of 10. In conclusion, we found out that En equals to the square root of 10 plus square root of 5. Then we know that O is the center of the circle, M is the point of the circle itself, therefore OM is the radius of the circle that is equal to the square root of 10 units. And what is the value of ME? From the drawing it is very easy to see that ME equals to MO minus EO. Again, MO minus EO equals to ME. ME equals to MO minus EO. So ME equals to MO, that is the radius of the circle and the semicircle, that is equal to the square root of 10 units, minus EO, that is equal to the square root of 5 units, that is one side of the square. So in conclusion, we found out that ME equals to the square root of 10 minus square root of 5. Okay? And we have already found out that EB equals to the square root of 15. In the next step, I presented to you rule number 2, and we implemented rule number 2 in our drawing. According to rule number 2, rule number 2 is true in any circle. So this circle could be any circle. So if chord AB, this is chord AB intersects with chord CD, this is chord CD in the red line, and the intersection point occurs at this point, point O, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN. This is chord MN that intersects with chord CB at point E. Again, chord MN intersects with chord CB at point E. Point E is the intersection point between the two chords. So we can implement here rule number 2. According to rule number 2, we'll get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. So actually I copied the two chords that intersect with each other here and the new drawing. Again, chord MN intersects with chord CB at point E. Point E is the intersection point between the two chords. Therefore, according to rule number 2, we get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. ME times EN equals to CE times EB. Chord MN intersects with chord CB at point E. Therefore, according to rule number 2, ME times EN equals to CE times EB. We have already found out that ME equals to the square root of 10 minus square root of 5. We have already found out that EN equals to the square root of 10 plus square root of 5. CE is the missing line segment, so we leave it as it is, times EB. EB is equals to the square root of 15 units. Okay? So in conclusion, we found out that square root of 10 minus square root of 5 times square root of 10 plus square root of 5 equals to CE times square root of 15. Okay? So in order to find out the value of this expression, first of all we substituted the two sides. Why? Because A times B equals to B times A, so square root of 10 minus square root of 5 times square root of 10 plus square root of 5 equals to square root of 10 plus square root of 5 times square root of 10 minus square root of 5. And according to rule number 2, it is equal to CE times square root of 15. According to the algebraic identity that A plus B times A minus B equals to A squared minus B squared, in our specific expression, A equals to the square root of 10, B equals to the square root of 5. Therefore, this side equals to a square minus b square, according to this trigonometric identity. So a equals to the square root of 10, therefore a square equals to 10, b equals to the square root of 5, therefore b square equals to square root of 5 squared, that is 5. So a square minus b square equals to 10 minus 5. So in conclusion, this expression in total equals to 10 minus 5, and according to rule number 2, it is equals to CE times square root of 15. 10 minus 5 is 5. Therefore, in conclusion, we found out that 5 equals to CE times square root of 15. We divided this equation by square root of 15, and we found out that CE equals to 5 over square root of 15. So here, the missing line segment CE equals to 5 over square root of 15. And what is the value of the line segment that we are looking for? That is to say, line segment CB. Line segment CB equals to CE plus CB. Okay, again, CB equals to CE plus CB. Here, CB equals to CE plus CB. We have already found out that CE equals to 5 over square root of 15 and EB equals to square root of 15. So the answer to the question is that CB equals to, this line segment CB equals to 5 over square root of 15 plus square root of 15. Here we simplify this expression in order to eliminate the square root in the denominator. We actually multiply square root of 15 by square root of 15, and then we divide it by square root of 15. We actually multiplied by 1, so we change nothing. In this way, we have a common factor with this expression. So CB equals to 5 over square root of 15 plus square root of 15 times square root of 15 over square root of 15. Okay, so in conclusion, CB equals to 5 plus square root of 15 times square root of 15 over square root of 15. So CB equals to, in the numerator we have 5 plus square root of 15 times square root of 15 is 15. So in conclusion, we have CB equals to 5 plus 15 over square root of 15. 5 plus 15 is 20, so in conclusion we found out that CB equals to 20 over square root of 15. Here we don't want that in the denominator we'll have square root, so we'll multiply this equation by square root of 15 and then we will divide it by square root of 15, so we change nothing because we multiplied by 1. So CB equals to 20 over square root of 15, so we multiply this equation by square root of 15, then we divide it by square root of 15, so we change nothing. In the numerator we have 20 times square root of 15. In the denominator we have square root of 15 times square root of 15 is of course 15. So we have this expression CB equals to 20 times square root of 15 over 15. Here we divided both the numerator and the denominator of this expression by 5. So here 20 over 5 is 4. So in total we have in the numerator 4 times square root of 15. In the denominator we have 15 over 5, that is 3. So in conclusion we found out that the length of this chord called CB equals to either 4 times square root of 15 over 3 units, or in terms of numbers, it is equals to 5.164 units. Okay, thank you very much.